So we're talking about the first derivative, and the one thing that we know is that when the first derivative is positive, that means the slope is positive, and that means the function is increasing. If the slope is negative, the first derivative is negative, and that means the function is decreasing. And so we can take the first derivative and we can find intervals over which a function is increasing or decreasing. So we have two examples. One of them is a nice polynomial example. Everything is beautiful. It's continuous everywhere. There's no discontinuities. Our second one is a rational example. Unfortunately, this rational example is continuous everywhere. In fact, there are no discontinuities in this one, but it does have some zeros. So we're going to break this down into interval tables. Here's the function x cubed plus 3x squared minus 2. Here's its derivative, 3x squared plus 6x. We factor it so that we can find the zeros easily. So this factors to 3x times x plus 2. It's a polynomial. It's defined everywhere. It doesn't have any discontinuities, so we don't have to define our intervals based on any discontinuities. We just have to go with the zeros. So we set our derivative equal to 0, and we just find that it is 0 when x is negative 2. We also find it 0 when x is 0 based on that factor. So these critical points end up being our boundary points for our intervals. Now, I don't have any fancy tools like a meter stick, for example, and so I've just got my interval table written out here in free form. So the intervals go across the top. Okay, so there's my critical point when x is negative 2, and this is everything when x is less than negative 2. Here's my second critical point when x is 0. This is when x is between negative 2 and 0, and this is the last interval, x being greater than 0. So we're going to find the sign of each factor in each interval, and then we're going to multiply them together to find out what the sign of the derivative is in that interval, and that tells us if the function is increasing or decreasing in that interval or not. Okay, so here we go. X is less than negative 2, so I can pick a test value. I can say, well, x is negative 3. I see that this factor is negative. 2x, when x is less than negative 2, like negative 3, that's negative 6. So that makes that negative. The derivative itself is now a negative number times a negative number. And so that's a positive number anytime x is less than negative 2. Okay. What about values of x that are between negative 2 and 0? So for example, negative 1. This factor, negative 1 plus 2, I can see that that factor becomes positive in that interval. 2x, so 2 times negative 1 is negative, so it's negative in that interval. So the derivative is negative in the interval from negative 2 to 0. So the original function is going to be decreasing in that interval. So I might like write a little decreasing there, except that I'd have to crawl around on the ground. So I'm not going to do it. Okay, when x is greater than 0, this is positive, this is positive, the derivative, positive times positive is positive. So the original function is increasing anytime x is greater than 0. So I'd be able to sketch some important features of the original function based on what I know about the value of the derivative in each of those intervals. Okay, let's go over to our second example. G at x is x divided by x squared plus 1. I take the derivative. I use the quotient rule. So bottom times the derivative of the top, subtract the top times the derivative of the bottom. And so this is x squared plus 1 minus 2x squared. That becomes 1 minus x squared on the top, x squared plus 1 squared on the bottom. Now, if this was a minus 1, this would give us critical points because the derivative would not exist if the bottom goes to 0. And so I'd have to count those critical points. This is always positive, though. It never becomes 0. And so I don't have any critical points that are where the derivative does not exist. I do have critical points, though, where the derivative is equal to 0. And that happens when the numerator is equal to 0. In other words, where those two factors are equal to 0, which is when x is -1, and so that's a boundary point, and when x is equal to -1, and when x is equal to +1. So those are the boundary points for my intervals. Okay, so I can put some test values into each of these factors, and I've included the bottom one, even though I don't really have to do that. So when x is less than -1, like -2, for example, this factor is negative. And when x is less than -1, -2, -2 minus 1 is -3. Change the sign. And this one's positive. Tricky devil. This one is always positive. So it's almost silly just to put it in there. And there is the sign of the derivative is negative, because a negative times a positive is a, times a positive is a negative. So the original function g at x is decreasing when x is less than -1. Okay, so x is between -1 and 1 in this second interval. So for example, 0 plus 1 is positive, 0 minus 1, and the opposite sign of that is also positive, and this is always positive. And so the derivative is positive, function is increasing in that interval. Finally, x is greater than 1. So this is definitely positive. This one, so for example, 2 minus 1 is 1. The opposite sign of that is negative. And that factor is always positive. Positive times a negative times a positive is a negative. The derivative in that interval is negative, and so the original function is going to be decreasing in that interval. And so that tells me some important information about how I could go about sketching that function. All right. Are there any questions? I take your no question. Excellent. Okay, I'll leave you to the homework. Bye.